everyone. Thank you for joining me today. My name is Itai Affe from Nielsen, and I'm going to talk with you about different streaming methods with Spark and Kafka. So a little bit about myself. I'm a tech lead in the big data group of a division within Nielsen I'll talk about in a minute. And I'd like to know a little bit about you. So how many of you are data engineers, data architects, something else? Okay, data scientists maybe? Okay, I'm just guessing. How many of you maybe attended our session yesterday about counting unique users with Druid? Oh, quite a few, nice. And how many of you are working with Spark and Kafka? Great, awesome. So let's see what our agenda for today is. I'm going to talk about the division I work for that's called the Nielsen Marketing Cloud and our high-level architecture. I'm going to talk about our data flow in the past and the present. I'm going to talk about stateless and stateful use cases in Spark streaming. I'll move on to Spark structured streaming, and I'll finish off with a kind of unique solution of streaming over our data lake. So the Nielsen Marketing Cloud is based on the acquisition of a startup called Exalate by the global company Nielsen a few years ago. Now, we are a data company, which means we buy and collect device-level data from all around the internet. So device can be your smartwatches, smartphones, smart TVs, you name it. And we collect the data, we enrich it using machine learning algorithms, and then we store it and make it available for our customers, which are marketers and publishers. And we allow them to do various operations, like better targeting their audiences and make better business decisions. At the Nielsen Marketing Cloud, we try to answer two main questions. So the first one is kind of the count distinct questions. So how many unique users or unique devices of a certain profile can I as a marketer reach? So if you're looking at the campaign for young women who love tech, the marketer can choose attributes of female, of a given age range and income that live in the US and are tech enthusiasts. The second type of question is a simple count question. So for example, how many impressions a campaign received? Let's look at the high-level architecture of our system. So from left to right, you can see here, we get events from both online and offline sources flowing into our front-end layer, which is called our serving system. We're talking about over 5 billion events per day. There we have some basic rules and more machine learning, more sophisticated algorithms that run and process the data and try to produce insights. For example, this device is used by a male from a certain place that's interested in something. This front-end layer is deployed in over 8 data centers around the world, and each data center has its own dedicated Kafka cluster. Now, all the raw data, all the events are written to the local Kafka clusters, and from there we have replication to our central Kafka cluster that's deployed over AWS in the cloud. The central of this architecture is the center of my talk today, is the big data layer, and we're going to talk about it today. From Kafka, we have various mainly Spark applications, some Flink applications. They do various ETLs to prepare the data and store it in various data stores, like Druid, which is our OLAP database, Clastrix, which is a distributed MySQL database, our data lake, our data warehouse, etc. The third layer is the applications layer, where we have our SaaS application, that's what we give our clients, to view the data and dissect it and look at it through various reports and real-time dashboards. Okay, so I'm going to talk about how we used to process the data, and I'm going to use this example throughout the presentation to show you how our data infrastructure has changed and evolved over the years. Now, this is a simplified example, but it will help me to show you what's actually been going on. So in the old days, I mentioned that now we have Kafka, but in the old days, what we had is our serving system, the front-end layer that I mentioned, writing events in the form of CSV files. Those CSV files were processed by standalone Java applications deployed on various machines. And those were stateless applications, just doing transformations and writing the data to our OLAP database. Now, previously, we used Clastrix, again, the distributed MySQL database, the operation database, as both the OLTP and the OLAP database. the stateful operations, like the in-database aggregations, were done on top of that database. So an example is we want to do aggregations on specific dates of specific campaigns, right? We want to collect and aggregate all the events that belong to a specific campaign of a specific date range. So what's wrong with that? So we had the two main types of problems. The first one was CSV-related issues. So first of all, we had issues of lines truncated within the CSV files because of multi-threading issues. But the more problematic issue was we couldn't enforce schema on the producer of the files. The second type of problems were related to scale issues. So we had to manually scale all those standalone Java applications in order to handle all the types of loads that we had. Moving forward, that's one small step for man a few years ago, and I would like to briefly talk about this quote at the bottom of the screen. So Derek Harris from Fortune.com said a few years ago that Apache Spark is the Taylor Swift of big data software. I'm guessing that it mainly said because Apache Spark was gaining a lot of popularity back in the days. And just briefly, because I saw that most of you are familiar with Spark, Spark is a distributed, scalable framework to process large data set in a kind of fault-tolerant way. And Scala is combining object-oriented and functional programming. So going back to the same example we had before, what we did is we replaced the standalone Java applications with Spark applications written in batch using the Scala language. And those Spark batch applications were deployed on top of AWS service that is called Elastic MapReduce, basically a way to deploy Spark and MapReduce clusters on the cloud. So why is this just a small step? So the good thing is it solved the scaling issues, right? Because Spark is very scalable, so we no longer had to manually scale our processes. The downside was it still didn't manage the CSV-related issues, namely enforcing the schema on the producer. Not sure how many of you are familiar with this character, Jed Bartlett from the TV series West Wing from about, 15 years ago. But it had a very nice catchphrase, what's next? So what was next in the modern way of data flowing? So the next step was to introduce both Kafka and Spark streaming. Again, most of you are familiar with Kafka, but just as a high level, it's an enterprise message bus platform, very scalable using a publish-subscribe mechanism. It was originally developed by LinkedIn, and one of the advantages for us, in addition to other advantages it has, is that it enables us to enforce the schema using the schema registry component and the Avro format for messages. Now, Spark streaming was a natural evolvement for our Spark batch applications. Now, Spark is a unified framework, right, for doing batch, streaming, machine learning, and stuff like that. So it was a natural evolvement from what we had before. And also, it works in micro batches, meaning that I can read, for example, the last 5 minutes or 10 minutes messages from Kafka and process them in kind of a streaming fashion. So let's see how it looks like in our example. Again, using the same example, now we've replaced two components. So we no longer have those problematic CSV files. Now we have Kafka messages in relevant topics. And we have Spark streaming applications rather than the previous Spark batch applications that read the messages 24/7, process them, and write them again to our OLAP database. That worked for stateless use cases. And all the left-hand part, as I mentioned, was working 24/7, right? It's a streaming application, so the cluster of the Spark and the Spark application itself was running 24/7. Whereas the right-hand side over here, the in-database aggregation, like I mentioned, say for various campaigns on various date ranges, were done in a periodic kind of way, for example, every few hours or once a day. So that worked for stateless applications, but going forward a few months, new requirements were being raised, and specifically this use case. So I mentioned that we use Clustrix, the distributed MySQL database, for both OLTP and OLAP operations, and this imposed a lot of load on the database. So what we needed to do is take the load off of this database and onto our Spark streaming applications, because we know that Spark is a very scalable framework. This slide is a bit complex, so try to bear with me. I hope it'll be meaningful for you. So we still have raw data, raw events coming into Kafka. Those are being read by the same Spark streaming applications, but what has changed? So first of all, now we do aggregations on top of each microbatch. Remember I said that Spark streaming works in microbatches, so now we do aggregations for each microbatch. And the result of that aggregation was written to the HDFS that is local to the Spark cluster that we ran. The next microbatch would read the state, right? Basically the previous microbatch aggregations, do aggregations of its own for the current microbatch, and write the combined result back to HDFS, and so on and so forth. So we had a state written on and on to the local HDFS. Now, remember, we need to update the OLAP database at some point, right? So every few microbatches, what we did is we wrote the data to our OLAP database and clear the state from HDFS. The way we wrote the data was using an upsert operation, and I'm not sure how many of you are familiar with it, but it's just a MySQL syntax that allows you to do inserts of new keys, and if those keys already exist in the database, you can just update their values. So the syntax is basically insert something, on duplicate key, update, and giving the values. So that's the upsert operation. This worked for stateful streaming applications, and we called it the way to do local aggregation, so to speak, because we used local HDFS in order to store the state. So what was wrong with that? Because obviously that wasn't ideal. The main issue was it required us to manage the state on our own using the local HDFS that I mentioned. It was error-prone because what happened if I lost my, if the EMR cluster was terminated and I lost the HDFS? It complicated the code, and it also imposed possible performance impact on our application. Say that I had delays in writing the data to HDFS or my database. It means that the Kafka consumer lagged, right, because of those delays. So, not very good. Luckily for us, in Spark 2.0, a new feature was introduced, or a new way to do streaming, that's called structured streaming. The main focus of structured streaming was to enable continuous incremental processes. So basically, it managed the state for you, which was really good for us. It was built on top of Spark SQL, and it was using data frame or dataset API. I'm imagining that most of you are familiar with it, but basically kind of doing tables or similar to relational database. And it was built on top of Catalyst Optimizer, which is a core component of Spark SQL that allows better performance of running SQL queries on top of Spark. It had many other features like handling event time and late data. But maybe the main focus here, as opposed to Spark regular streaming, is that it handled the end-to-end exactly once fault tolerance on its own. And also for us, because we are early adopters and you saw that we had issues, we really embraced it, even though it was in alpha mode in Spark 2.0 and Spark 2.1. So let's see how it worked for us in our infrastructure. Again, going back to the same example, then we still have messages in Kafka, but now rather than having those Spark streaming applications, we have Spark structured streaming applications doing what they call window instead of microbatch, but the idea is the same. So we aggregate the data on every window. We write checkpoints, and I'll talk about checkpoint in a second, sorry. We write checkpoints to S3 buckets, right here. And then we upsert the data as before to our OLAP database. Let's talk about the checkpoints for a minute, because in this example, Spark structured streaming handles the checkpoint for us. So checkpoint is just a way to persist your state of the application. And the state means both the state of the aggregations or the stateful operations that you do in your application, but it also means storing the offsets you already read from Kafka to the same persistent store. So Spark structured streaming made it available for us, and this is the way we did stateful applications in structured streaming, but we also did it for other use cases. So because we are early adopters, we obviously hit some major roadblocks with Spark structured streaming. I'm not going to talk about every one of the issues here, but just to give you an example, one major problem that we had is that if we had more than a few partitions in our Kafka topics, which is obviously what you usually have, then the application wasn't able to recover after crashing. So that was a major block. Another thing we had, I mentioned that we used S3 for checkpointing. Now, probably some of you know that S3, as well as other blob stores in various cloud providers, are not really file systems, right? They provide you with a file system-like API, but they are eventually consistent. And this is a problem when you do checkpointing. So the way we try to mitigate that is we try to use a solution on top of EMR, AWS service, that's called EMR First Consistent View. Don't worry if you're not familiar with it. The idea is just to allow you to have a sort of more consistent view of S3. So that worked really well for stateless applications, but for stateful applications, we had sporadic issues. So again, that wasn't enough for us. Just to summarize some of the strengths of weaknesses of Spark structured streaming, in my opinion. So the strengths include running incremental continuous processing and basically handle state for you. It includes increased performance via Spark Catalyst Optimizer. And maybe one of the biggest benefits is that massive efforts were invested in it from the entire Spark open source community and DataWorks themselves. On the other hand, weaknesses were mostly around maturity, so again, not ideal for us, and we needed to rethink our infrastructure again. Now, going back to the future, so to speak, in this point, we revived Spark streaming applications, even for stateful applications. So going back to the same example, what we replaced now? Again, same Kafka with same raw data, raw messages. But now we went back to Spark streaming applications, doing aggregations on the current microbatch level, and writing the aggregated data to S3. So that was one component what we replaced. Another component we replaced is, if you remember, we used Clustrix, the distributed MySQL, as our OLAP database. But now what we've done is we basically introduced Druid, which is a time series database, which is much more suitable for OLAP use cases, and we integrated it into our tech stack. Something that's important to note here that those Spark streaming applications and the cluster they are running on are 24/7 running applications, right? So we pay for those EMR clusters as long as they are up and running, which is basically all the time. So that was cool, that worked, but we couldn't stop here, right? That's not enough. So let's talk about a few problems we had. So the first problem that we had is we had significantly underutilized clusters. So I didn't mention it earlier, but we used very large micro batches. So micro batches of 1 hour. And the reason is the longer your micro batches, the better aggregation ratio you can get, right? If I have, for example, 300 million messages for 1 hour micro batch, I can maybe aggregate those into, say, just 1 million rows for output, right? So I get a really good aggregation ratio. So we wanted to use long micro batches. And for long micro batches, you can see in the CPU usage here that around 20 or 30 minutes of the time, the cluster was actually being utilized. And the rest of the time, it was idle. So that was just wasted money, okay? Because in cloud and in other environments as well, you just pay for resources, whether you use them or not, so wasted money here. But that's not it. We also had extreme load on Kafka Broker's disk. And let's talk for a minute on how Kafka stores the messages. So obviously, Kafka can store in memory only some of the messages, right? Say the last minute or last 2 minutes or something like that. But when you have very large micro batches like we had, most of the messages that you want to read are already persisted to disk. So when you want to read them, you need to retrieve everything from disk. Now, we are talking about multiple applications, right? We don't only have one application. We have multiple applications doing large micro batches. So that's a significant load on Kafka disks. Another thing we had is we were using Spark streaming with Kafka 0.10 integration. And that resulted in weird concurrent modification exceptions. Now, that forced us to use only one core per executor, which, as probably most of you know, isn't really efficient with Spark. And the last thing is that we wish we could run it even less frequently, because remember, the longer the micro batch, the better aggregation ratio we can get from it. So after some homework we've done, we introduced a new and unique solution of streaming over our RDR. You probably ask yourself, okay, what is RDR? So RDR, or raw data repository, is basically our data lake. The way it works is the following. We have events flowing into the relevant Kafka topics. And from there, we have lightweight stateless Spark streaming applications called RDR loaders, which basically read the data and store it in our data lake in a Parquet format. Now, the important thing to note here is there's only one application per topic, right, in order to read the raw data from Kafka and store it in our data lake. And also, because they are stateless applications, I don't need to run large microbatches. I can run relatively small microbatches, like every 4 minutes or 6 minutes. From our data lake, applications can read the data and do various, or be used for various use cases. So one example and a very common use case for us is reading the last 30 days from our data lake and analyzing it. So the question is, can we leverage the data lake and use it as the data source instead of Kafka? Well, the answer is obviously yes. And let's see how we do it. So on the producer side, what we have is we have our RDR loaders, basically those lightweight Spark streaming applications, reading the data from Kafka and writing it to S3 buckets, which are our data lake. But on top of that, what we also do is we write the file names or the file paths of S3 to designated Kafka topics, right, which are much smaller. They only include the file names and not the raw data. Now, you might ask yourself, why did you choose Kafka and not, for example, a regular queuing service like SQS? So the reason is, as I mentioned earlier, we have multiple applications that need to access the data in the data lake, right? So SQS or regular queuing service wouldn't work here, and we need something that's more publish-subscribe, and that's why we chose Kafka for that. So that's the producer side. On the consumer side, we have, as you can see, Spark batch applications that consume the file names from the designated Kafka topics. They can read the actual files based on what they just read from Kafka from our data lake, and then they can process the files and do whatever transformations and aggregations they want to do on top of it. Now, the nice thing here is that these clusters are transient, right? I can launch my Spark batch application, say every 3 hours, 6 hours, once a day. The cluster is going up, running that application, and as soon as the application is done processing the data, the cluster can be terminated and we can save money as a result from that. Another thing we've replaced is we no longer use the Spark streaming plus Kafka integration because we only need to read the file names and we do it from the Spark driver using the regular Kafka API and then storing the offset again in the regular way, committing them and maintaining them in the same way we do for every Kafka consumer. So how does it look like in the example that we walked through the entire presentation? So now we have those designated Kafka topics with the file names being read by the Spark batch applications, and those Spark batch applications can read also the appropriate files from our data lake. From there, we do the same aggregations, writing the data to S3 buckets and loading them periodically to our OLAP database, which is now Druid. So did we solve the aforementioned problems? I mentioned that one of the biggest problems was cost. So because our Spark clusters are now transient, as I mentioned, there are no more idle clusters. Let's look at the cost in the previous and the current solution. So in the previous solution, in the old Spark streaming application, we used to pay around $1,000 per day, and the cost is fixed. And it is fixed because the Spark streaming application is running 24/7. We're paying for the cluster as long as it's up, and it's up all the time. So the cost is fixed. As opposed to that, the new infrastructure, the cost isn't fixed and it's much lower. Let's see why. So for once, it's much lower because now I can terminate the Spark cluster as soon as the application is done. So I save the cost on underutilized clusters. Another thing we felt comfortable of doing is using spot instances, which is, I don't know, similar to preemptive instances if you're using Google Cloud or stuff like that. And we felt comfortable doing that for batch applications, right? Because now we use Spark batch applications, and felt less comfortable doing that for streaming applications. So you can see we're talking about a cost reduction of over 80%, which is significantly, which is a very significant cost reduction when you're talking about a lot of applications that are running every day. Now, why is the cost not fixed in the new infrastructure? Because now, as soon as the application is done, we terminate the cluster. So if we had more data to process that day, we paid a bit more money, like you see in day 2, right? This is closer to $200 a day. But if we had less data to process that day, and it happens, right? You have spikes, you have downs, so we paid a bit less in day 1 because we had less data to process. So check for that for the first problem. What about the load on the Kafka disks? So now, because we only have one application reading from the raw topics in Kafka and storing them in the data lake, and those applications are lightweight, all the other applications can just read the file names from Kafka, and we're talking about around only 1,000 messages an hour, which are containing only the file names. So even though we have a lot of applications reading those file names, we are talking about relatively low volume of data. So this solved the problem of extreme load on Kafka disks. I also mentioned that the new infrastructure no longer uses that Spark streaming plus Kafka integration, so no more weird exceptions and no more need to run only one core per executor. And now, because we're using Spark batch applications, we can run them as frequent or infrequent as we'd like, and get the aggregation ratio that we want to get. Okay, so just to summarize here, we initially had standalone applications, Java applications, reading CSV files, and we quickly transformed them into Spark and Scala applications, but we were still left, this solved the scalability problems, but we were still left with the CSV-related problems, mainly couldn't enforce the schema on the producer. After that, we introduced Spark Streaming and Kafka for stateless use cases. So now we could enforce schema on the producer of the messages, but quickly we needed to handle stateful use cases as well. We tried to do some kind of local aggregations for Spark Streaming stateful use cases, but that required us to manage the state on our own, which was really not ideal. Because Spark Structured Streaming had so many promises, we moved and introduced it in our tech stack for most of the use cases, but unfortunately, at least at that time, it wasn't mature enough. Then we went back to Spark Streaming and introduced Druid as our OLAP database, but still it had issues because it imposed performance penalty in Kafka for long microbatches, it had underutilized Spark clusters, and many other disadvantages. And finally, we introduced rather unique solution of streaming over a data lake. So that eliminated the Kafka performance penalty. It saved us a lot of money and had many other advantages. Cool, so just before I wrap things up, a few things we care about. So we are currently building the Israeli chapter of a worldwide program that's called Women in Big Data that aims to inspire, connect, grow, and champion success of women in big data. And the goal is to increase women representation in that field to over 25% by 2020. For those of you who weren't here yesterday for our count unique users in real time, the presentation and the recording should be up there in a few days. And last but not least, we have a tech blog, the NMC tech blog, where we try to write about the interesting things we do around the NMC. That's it for me. And I'll be taking questions now. Yeah, sure. Thank you. Thank you very much. Maybe you can just step up to the mic.
Hi, I would like just to know why have you choose Druid for OLAP and not another system? For instance, you are on AWS. It provides also, I forget the name. It provides a database for OLAP. So it provides. So why have you choose basically Druid?
Well, it goes a bit back to the presentation yesterday, but basically Druid has first of all, it's very suitable for OLAP, and second of all, it's very good and it has a built-in support for doing, say, solving the count distinct problem using an approximation algorithm that's called theta sketch. Now, I mentioned in the beginning of my presentation that one of the main questions that we need to answer in our application is how many unique users of a certain profile we can reach. So we do that using Druid's theta sketch algorithm, and it gives us very good results. So that's the reason why we went on with Druid as the all-up system. Yep. You want?
It's too far away.
Okay, I'll just repeat the question. Yeah.
You said at the end that you left out the integration between Spark and Kafka, and you access directly the Spark driver.
Yeah. Okay. I'll explain that. So the question was, why did we stop using the Spark and Kafka integration and read messages from Kafka directly from Spark driver? I agree it sounds a bit weird, but the reason is that in the new infrastructure, we only need to read the file names from Spark batch applications. So we read, say, I don't know, 1,000 messages in the driver, and then what we do is we process the files using, Spark read parquet, giving all the paths, and then the work is distributed across the Spark cluster, right? So we no longer need to use the Spark and Kafka integration because we are no longer reading the raw data from Kafka, only the file names. Make sense? Yeah, go ahead. Yeah, sure.
Yeah, thank you. Very good presentation. I like the pragmatic approach. I have one comment and one question.
Sure.
About the issue you mentioned for Kafka and the disk, this is exactly the same conclusion the guy from Apache Pulsar they have. And that's why they split the transport of the data from the storage using Bookkeeper, and then you can plug any backend you want, like S3, for instance. So by using Pulsar, you could have exactly the same advantage as using one queue having the storage, while still decoupling the storage on S3, right?
Yeah, I'm not familiar with Pulsar, but sounds reasonable. Yep.
Okay. So, and then question, so on streaming and stateful streaming, well, we always compare Flink and Spark on the statefulness and the advantage on stateful management. So what's your point on that?
Okay, that's a very good question. So first of all, to be honest, I'm familiar with Flink, but just a little bit. But I think the main thing is we started off with Spark Batch when it was, just, I don't know, 1.0 version. So really early on. And because it's a unified framework, it made sense for us to go with Spark streaming. So for us, we don't really need like very, very low latency, I don't know, fraud detection streaming, right? We can do micro batches, and it's good enough for us, so it makes sense to go with Spark streaming.
Makes sense. Thanks.
Sure. Yep.
Just a question about the ingest
Yep.
Spark streaming into S3.
Mm-hmm.
How much was that to keep running?
How much what?
Had to be permanently running? The ingest from Kafka into
Yeah, so
S3.
in the new infrastructure, we only have one application per topic, and those are lightweight applications. They only read the data, do like really lightweight transformations, writing the data into our data lake, and from there it can be consumable by any other application. So those are really, rather small application doing small micro batches.
Thank you.
Yeah, go ahead.
Why you use Kafka? Why you don't use service from AWS like Kinesis, Kinesis Stream or Glue?
Okay, that's a good question. So I showed the architecture when we started the presentation. The thing is, we have we kind of hybrid cloud solution, right? So we have our front-end layer, the serving system, deployed in 8 data centers around the world, and we have the big data layer deployed on AWS. So I need an infrastructure that can push the data from the various data centers into the main the main cloud. So Kafka deployed in the various data centers, the local Kafka cluster, and from there we have a replication to the central Kafka cluster. That's the reason why I can't use Kinesis, because I'm not deployed only on AWS. Answer the question? The other question? Yeah, go ahead. Which tool I use for the Kafka replication? We actually took a kind of fork of Uber that's called, I think, UMiro or UReplicator. Okay. Any other questions? So, yeah. For the aggregation, yes. Okay, so the question was for the aggregations, why use Spark streaming and not Kafka streams and stuff like that. So again, it goes to the same reason of we had Spark. It's a unified framework, so it made sense for us to have the same code repository for the business logic and everything. And also, when we started with it, there wasn't any Kafka streams. It wasn't even early on. I think it didn't exist even. So that was the main reason. Yeah.
So I got a question regarding the triggering the application.
Regarding what?
Regarding the triggering of the application, the batch processing of the Spark.
Yeah.
So yeah, it was the question. In the Spark structured streaming, there is an option to trigger the application once. At this time, at this moment, particular, did you consider to using this and don't resign from the structured streaming to using the triggering once only the application if you're running the cluster, or?
I think it's a rather new option.
It's since the triggering once is from the 2.2.
Yeah, so
So
rather new. I'm talking about we left
1 to 1, right? Okay.
Yeah, from one, but that's the reason. And also, we want to be able to shut down the clusters as soon as the application finishes to save money. So.
Yeah, but I think there is actually there might be a problem with the offset management from the Kafka. But yeah, I just wondering, did you consider it to update the application to do not use the batch processing and still going with the structured streaming regarding the?
No, because again, we want to be able to shut down the clusters. I need to reduce, reduce the cost. I need to shut down the cluster. And if it's Spark structured streaming, I'm guessing you'll have to pay.
Yeah, but I think there might be an option. I'm not sure about that, but I think you can somehow save somewhere last offset which you have processed, and then you can shut down the cluster. And if you spin it up again, read the last offset which you have been started, ended, and start from this point, yeah, with the structured streaming using, and not use the old.
The old
yeah, all the way. Yeah. Okay. Thank you.
Thanks. Yeah.
So your approach seemed to be very, very logical and planned right from the beginning. Was that really planned, or was that also trial and error?
No. The question was the approach planned. So I think, as with probably any data infrastructure out there, and more so when when you're an early adopter, then you just have to adjust to what the open source world has to offer you, right? So yes, when I joined, we had those Java standalone, and I think one of my first tasks in the team was, okay, this is Spark, it's not running on AWS, please make it run on AWS and somehow do the magic of running it. We had a lot of communication with AWS teams in order to actually being able to run Spark on AWS, something that today you can just do on a click of a button. So we just had to work with it, and we encountered, as you've seen, as we added new features to our infrastructure, we had new requirements from product and from our customers, and we had to grow our stack and stuff like that. So I can't say it was planned from the beginning. No, I won't be able to take that credit. No. Cool. So I hope it was enjoyable for you, and if you liked it, please vote in the application and rate the presentation. Thank you very much for your time.